Aliens calling. Your feed loves that headline. I get it. The universe is wild, and I live for wild stories. I'm Riley Rush. I used to chase tornado footage and interview storm chasers at 3 a.m. Now I chase clean truth in space mysteries. Tonight I break down 8 real signals that sparked the alien talk and show what they really are. You get the wonder without the hype. I dug through old telescope logs, mission releases, and the original papers, so we stay honest. By the end, you will know the playbook scientists use: repeatability, dispersion measure, frequency drift, polarization, independent confirmation. These tools cut noise from signal. We even set the stage. Back in 1961, Project Ozma tried the first modern search for radio life. Since then, radio dishes became our ears. One frequency matters a lot: the hydrogen line, near 1420 MHz. SETI fans call it a universal hailing spot. Here we go. First up is a metronome in the sky from 1967. A tick every 1.33 seconds. The team even nicknamed it Little Green Men. This is crazy top 10, and we do this right. Before we dive in, do you think they really heard Martians? Drop your gut take, then ride along. Number 1 is a legend, and its twist changes everything. Number 1 starts with a perfect beat from the stars. November 28, 1967, a grad student named Jocelyn Bell Burnell spots a radio source that blinks like a clock. Click, 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 every 1.33 seconds. The timing is so clean, the team jokingly writes LGM1 on the chart, Little Green Men. For a night, that idea is on the table. Then science kicks in. They check the equipment. They point the array again. The pulses show the same rhythm at the same spot. Soon, other blinking sources appear in other parts of the sky. If one beacon looks unusual, maybe it is a prank. If many show up, it is a new class of object. Repeat it or doubt it. That is the rule. The answer lands fast. LGM1 is not a message. It is PSR B1919 plus 21, the first known pulsar, a neutron star that spins and sweeps a radio beam like a lighthouse. A collapsed star, dense as a mountain packed into a city. The beats are the spin, not a code. I love this case because it builds the first refrain. Patterns matter, and more than one source seals it. Keep that in mind as we move to a one-time blast that still haunts us. Number 2 is the famous wow signal, a clean radio spike that hit like a gunshot. August 15, 1977, Ohio State's Big Ear telescope scans past a patch of sky. For 72 seconds, the receiver sees a strong narrow band tone near 1420 MHz, the hydrogen line. Astronomer Jerry Eman circles the printout and writes a single word: wow. Why is that frequency a big deal? Hydrogen is the most common element. Many in SETI use that line as a natural hailing spot, the place any curious mind might choose to call. Back in 1961, Project Ozma picked it too. The Big Ear spike looked exactly like what a steady transmitter would produce, as Earth's rotation swept the antenna past the source. Then comes the cold part. It never came back. Teams returned with bigger dishes and longer watches. Nothing. No repeat. No second hit. One time is a red flag. Without repeatability and a second telescope hearing it, we cannot test direction or motion or polarization. It stays unexplained, not confirmed. To me, the wow signal is a perfect cliffhanger. It invites wonder, but it teaches caution. Now watch how a new class of millisecond flashes pushed us forward. Number 3 explodes in milliseconds. In 2007, astronomers digging through old data found a burst that lasted only a few thousandths of a second. It was bright and brief. That spark started a flood. We now catalog hundreds of fast radio bursts. For that blink of time, some outshine whole galaxies in radio. Here is the key clue. These bursts arrive smeared across frequency. The low notes lag behind the high notes. Space is full of thin plasma that slows radio waves a tiny bit. The total delay is called the dispersion measure. Big delay means a long trip through a lot of plasma. That points to sources far outside our galaxy. Then it gets even weirder. A few FRBs repeat. FRB 121,102 popped again and again from a dwarf galaxy. FRB 180,916 even showed a cycle, like a pattern that turns on and off on a schedule. Repeaters rule out one-time disasters for those sources. That hints at engines that can survive. Magnetars, young neutron stars, or other extreme objects. The best part is that repeaters let us point multiple dishes and test the physics. Independent confirmation turns a mystery into a lab. That set the stage for a breakthrough right in our own Milky Way. Number 4 delivers a eureka moment. On April 28, 2020, a magnetar inside our galaxy let loose. The source is called SGR 1935 plus 2154. A magnetar is a neutron star with a magnetic field trillions of times stronger than Earth's. When it sheds energy, it can crackle in X-rays and radio. 2 radio arrays, CHIME and STARE-2, caught a burst from this magnetar at the same time as X-ray flares. The radio flash lasted milliseconds and showed a dispersion signature, just like an FRB. The distance is about 30,000 light-years. Because it is so close, the burst hit us hard, yet its energy was about 1,000 times weaker than the big extragalactic FRBs. Put it in a faraway galaxy, and it would look like a classic FRB. This was the first direct link between an FRB-like burst and a known object. No message, no code, just an angry dead star snapping its fields. Since then, the same magnetar has flared again. Repeat and verify. That is the refrain. If this kind of space detective work fires you up, subscribe for more smart mysteries with me. Now, remember, not every weird blip comes from the sky. The next one came from lunch. Number 5 is my favorite plot twist. At the Parkes Radio Telescope in Australia, scientists kept seeing spiky bursts near 1.4 gigahertz. They looked a lot like FRBs, but something felt off. They appeared in many directions at once, and most often around lunchtime. That is a clue only a detective loves. The team set radio monitors around the site to sniff out local interference. They watched the control room and the kitchen. Then they caught it. Every time someone yanked open a microwave oven early, before the timer ended, the shield leaked to pulse right into the telescope. The staff had invented a fake space signal with leftovers. They called these imposters Perytons, after a mythical creature that looks real but is not. It was the best kind of embarrassment. It forced a cleanup of habits and hardware. Observatories tightened radio filters, mapped their own radio noise, and logged every test. The result made future searches stronger. File this under humble pie. Not all strange bursts are cosmic. Sometimes the culprit is the break room. Hold that lesson tight, because the next candidate came from the direction of our nearest star. It looked legit at first, and it fooled many pros. Number 6 zooms in on the closest star to the Sun. In 2020, the Breakthrough Listen team reported a signal in data from 2019. It seemed to come from the direction of Proxima Centauri, just 4.2 light-years away. That would be the backyard in cosmic terms. They named it BLC-1 for Breakthrough Listen Candidate 1. It sat at about 982 megahertz. It stayed narrow and steady for hours. It even drifted slowly in frequency the way a transmitter might drift if it sat on something that moved. The candidate passed early filters and lit up the rumor mill. Then the hard checks rolled in. Analysts found near-identical tones when the dish pointed at other parts of the sky. That breaks the sky test. They also linked the tone to other weak patterns that screamed human technology. The most likely cause was a microwave link or other gear on Earth or a satellite sneaking into the receiver. Once again, cross-checks and independent looks saved the day. BBC One was not a call from Proxima B. It was a lesson in rigor. Pass every test or it does not count. Now let us head to the crowded heart of the Milky Way for a puzzle that still refuses a label. Number 7 lives near the center of our galaxy, where stars pack tight and clouds stir. Over the last 2 decades, radio telescopes have found odd transients close to the core. One famous case is named GCRT-J1745-3009. It turned on, flashed for several minutes, went quiet, and then vanished for months. These sources do not behave like normal pulsars. They do not follow a simple period. They do not keep a steady pattern. Some pop up once or twice and never return. Others show short clusters and then long silence. They could be rare neutron stars, strange magnetars, or clouds near the central black hole playing tricks with radio waves. Right now, the data is thin. What do we do with thin data? We stay patient and build better ears. Arrays like the Square Kilometre Array and the Next Generation Very Large Array are designed to watch wide areas for long times. Catch more events, compare polarizations, chart frequency drifts. With enough catches, the pattern might reveal the engine. Until then, the galactic center blinkers remind me that discovery often starts messy. We know the signals are real, we just do not have enough repeats yet. One more mystery remains, and it made front-page MIFs. Number 8 is not radio at all. It is a light curve from a sun-like star named KIC 8,462,852, also called Tabbys Star. In 2015, the Kepler Space Telescope recorded the star dimming in wild, irregular ways. Some dips hit about 22%. For scale, a planet the size of Jupiter would only block about 1%. The idea machine went into overdrive. People talked about an alien megastructure, like a Dyson swarm, orbiting and blocking the light. It sounded bold, and it looked dramatic. But bold ideas need more clues. Teams searched the star in infrared and in radio. They did not see the extra heat a giant structure or thick dust cloud would give. Later, they measured the color of the dips. Blue light faded more than red, which is a dust fingerprint. The best fit today is clouds of fine dust or broken comets drifting around the star. They are irregular and changeable, which explains the random dips. No beacon, no code, just strange shadows in space. This story is a perfect capstone. Go wide, get data in many wavelengths, and test the simple ideas first. With that toolkit in hand, let us land this tour with the key takeaways. 8 strange signals. 1 clear lesson. Space is full of surprises, but hype fades when tests begin. The gold standard is repeatability. Pulsars repeat. Some FRBs repeat. That lets us cross-check and confirm. One-time hits like the wow signal, or a single Proxima candidate, need extra caution. Here is the toolkit you now own. Use dispersion measure to sense distance through space plasma. Watch for frequency drift to catch motion from spin or orbit. Check polarization for magnetic clues. Above all, demand independent confirmation on another telescope. If the same blip does not show up again, or does not show up elsewhere, it is probably noise or Earth-based. I host this because I love the story, but I respect the evidence. This is Crazy Top 10, and our promise is fun plus facts. Thanks for riding along with me. Like the video, share it with a friend, and tell me in the comments. Which story surprised you most? If you want more wild mysteries told straight, subscribe and turn on the bell. Thanks for watching, and keep your eyes up. The next real signal could hit our dish any day.